All right. Good afternoon, everyone. Joining us this afternoon. We're very happy to resume here with a couple of talks before the end of the day. And first, we're going to have Ricardo Baptista. He is joining us from the University of Toronto. Prior to that, he was at MIT and also was recently at Caltech. And we're very much looking forward to this presentation on contrastive learning.
Thank you very much, Chad, for the nice introduction, and to the organizers for inviting me to be here today. It's really been great to have a lot of discussions so far. And what I want to do today is talk a little bit about something that's been brought up in a few other talks, this methodology of contrastive learning. And hopefully everything is set. Great. It also connects with one of the themes that Anne mentioned yesterday of how do we build models for multimodal data. And that's actually how I was first exposed to this topic when I learned a little bit about multimodal large language models and how they're now taking in various different types of data like images and prompts and learning somehow to relate the two. And I was fascinated by this and I wanted to understand it a bit better from a mathematical perspective. And this is my humble attempt to do that. As part of the talk, I want to show how this can also be used as an maybe unconventional approach to solve inverse problems. So, and that is both in the context of image and text data, but also for other types of data in the sciences. Before I get started, I want to acknowledge my collaborators. This is a joint work with Andrew Stewart and San Tran. So this is work that was done while I was at Caltech before joining Toronto this past year. So as a starting point, I want to show just some examples of how this methodology is being used in first in a data science context. And so the two kind of most prominent examples are in trying to generate images or trying to process images. So first, we're seeing a lot of models, in particular these prompt to image models that can take in a prompt like a cat and a frog and learn to generate images that we see here. For this particular example, I generated these images using a stable diffusion model, which has a lot of different components, but inside of it is some model that can relate this text prompt to this image. That says that these two things are somehow different representations of the same thing, and knows that, for instance, if I write that I want a large aircraft taking off, that there should be a picture of this aircraft that has at least 3 engines on one side and is maybe asymmetric. Another example is what's known as VQA, or vision question answering, which is this task of multimodal models of taking in an image like the one that we see here, as well as a question of what kind of flower is this, and learn to process these two and interpret that this is a forget-me-not flower, or even more involved, take this picture on the right that has some text written in Portuguese. And when I ask what is the text, the model is able to first determine that it's text written in another language, read what the text is, and then translate it into English. And just like in the previous example, this relies on having some way of relating this piece, this image, to this response that's given here at the bottom. So there's some model that's being learned in order to relate these two types of data to each other. And this, for most of these multimodal models, this is based on a methodology that was introduced in 2021 by Alec Radford and collaborators at OpenAI. It's often referred to as CLIP. This is an acronym standing for Contrastive Learning Image Pre-Training. I always look up how many citations this paper has right before I give this talk. So this paper, as of yesterday, has 61,000 citations. Just for reference, I gave this talk in October, and it had 44,000 at the time. So it's growing at a very quick rate, maybe on the order of about 2,000 a week, something like that. And fundamentally, the idea of this model is that it tries to construct a way of outputting a similarity score between two types of data. So between, for instance, text like a large white jumbo jet is parked on an airport runway, and a picture like the one here in this first column, where it's going to build, what this methodology does is that it builds a model that can output a number, in this case 0.28, number between 0 and 1, that says that these two different representations are more similar to each other than this text is to, for instance, this image of bananas on some holder. But this is a similarity score. So if we look across this row, it also tells us that this piece of text is maybe, even though it's not very related to this image, it's kind of partially related to this image given here. And you could kind of interpret that from the fact that they both of these images involve an aircraft, and this text is maybe partially related to that last image. So the goal of this model is to be able to compute something like this similarity matrix between all pairs of text prompts and images. Now this allows us to do many different tasks, like the ones that we saw at the beginning. It also allows us to solve tasks like retrieval, where you then put in, you take a big database, you put in a text prompt like a cat and a frog, and try to get out an image. In this case, I did this with the MS Coco data set. Sometimes this works, like for these 3 examples here. Sometimes it doesn't, because it associates certain parts of the prompt with certain objects that share some similarities with the prompt. In this case, that both a frog and this pen are green. But in many cases, this does work very well. And in particular, it allows us to solve this retrieval problem. Can be thought of as solving a type of inverse problem that takes in a text prompt and outputs the most similar image in a database, which is also useful for scientific tasks. So if, for instance, we get some data that tracks the positions of sea ice flows in the ocean, one inverse problem that oceanographers are very interested in is to try to back out what is the ocean currents that led to a particular trajectory for the sea ice flow. And this can be solved, and what I will show you today is that we can apply a similar methodology to tackle this problem, because we can see the two different types of data, like the positions of sea ice flows as a trajectory, as one type of data modality, and another data modality as the ocean currents, these fields, something similar to like text and images. So in the talk today, I want to describe how this methodology works in a few different parts. I want to describe first the problem of actually learning this model, provide some analysis behind it, and then lastly present some numerical results primarily in the context of this inverse problem. So first, for the learning problem. So for this, I'll introduce a little bit of notation. I'll present this all in the context of text and images, but it does also extend to these to more general problems. So for today, we're going to represent text as a variable u in some kind of space, mathcal u, and images v in this space curly v. And we're going to assume that we have some pairs of data samples of text and image these are paired together. So UI and VI, we collect some IID samples from some joint distribution of text and images. And the way that we are going to construct that or compute those similarities between text and images is by finding a way of encoding the text and the image in a space of the same dimension. In particular, we're going to look for encoders GU and GV that map from the space of text and images into a common, typically low-dimensional embedding space of dimension NE. Now, these encoders, there's typically a lot of different architectural choices that are made for these encoders depending on the type of data that we're working with. I'm not going to focus on that today. We're just going to focus on trying to understand what exactly is computed when we look for these encoders at the functional level. Now, if we look at some of the code for that is typically produced by for finding these encoders, the objective function that we're going to find to learn these encoders is something that looks like this, and I'm going to parse what are the pieces of the objective function that appear here. So what is commonly done to find these encoders is to maximize a loss L. I call it here L clip of theta. Theta is going to represent the parameters in both the encoders for text and for image, GU and GV. And what this objective does is it has three parts. The first part computes the similarity, the inner product between the encoding of text and image that are paired to each other. So think of that picture of the plane and the text prompt associated with the plane. We're going to encode both of those types of data, measure their similarity, and maximize the inner product, the similarity between paired text and images. That's the first term. And then the second two terms, what they do is they take every text prompt, UI, and all other images, not necessarily the ones that are related to this text prompt. So for instance, the text of the airplane and the image of the banana or the image of all the other objects. And they try to minimize the inner product or the similarity between the encoding of these pairs of samples. So the idea is that we want to maximize the alignment between paired samples and penalize or minimize the alignment between unpaired samples. So this objective, intuitively, it sort of makes sense. But our goal was to really understand is there something maybe more fundamental behind this type of objective? Yes.
Is there a reason for this log sum exponential thing?
So at this point, no. But I will. One can definitely. There is a probabilistic reason behind it that I will try to argue. Thank you.
Aren't these two terms the same, or am I missing something?
No, thanks for checking. So the only difference is whether is the indices for the sums. So here, this is over I. So it's over for every text prompt, you measure the similarity between all other images, and then the other one, you fix an image, measure the similarity with all of the text prompts. Thanks. Okay. So what I want to present is what this looks like at the population level rather than at these individual sample levels. And to do that, so we start out with just a distribution mu for where our data came from. So I'm going to call that our data measure mu, the joint distribution of images and text, which has some marginals. I'll denote that by mu u, mu v, and also some conditionals, mu of u given v and mu of v given u. So this is the conditional distribution over, for instance, mu of u given v of all text given a particular image. And what I'm going to define is a target distribution, nu, which takes the two marginal distributions for text and image, mu u and mu v, and multiplies it or tilts it, if I can use that term, by a density rho, which depends on both U and V, and is constructed based on the exponential of the inner product between the encodings of GU and of text and image. What this tilting does is essentially it defines a way of correlating or relating these two variables, U and V. Underlined, given this target measure, nu, I can compute conditionals of image given text and text given image, and I'll similarly denote that using these subscripts of U given V and V given U. Now, at this, given this formalism, I can define objectives to learn the parameters of this approximate distribution nu in order to match the data distribution mu. In particular, one objective that one can construct is to say, if I have the true conditionals mu of U given V and V given U, I can measure some divergence between those two conditionals and the conditionals under my model, parameterized by theta. In this case, because these conditionals depend, for instance, for text given image, depend on every image, I should also take an expectation over images. Similarly, for this second term that looks at how well I match the distribution over images given every text prompt, I should take an expectation over the text prompts. And given this objective, you can minimize it in order to find the parameters. If you had a sufficiently rich model, then it would exactly match the conditional distributions under your data. Now, while this looks kind of contrived at the moment, the reason why we arrived at this objective is because if you do some simple calculations and you unpack under the particular data model and approximate model that we wrote down, the objective that you would minimize J here, you can actually write it, the optimization problem, as being equivalent to one where you maximize an objective L, which is precisely the population level objective of what's written down in the, at least in code, when trying to find these encoders. An objective that would maximize the alignment between samples that are jointly drawn from mu and penalize the alignment between samples that are drawn independently from the tensor product distribution of images and text. So this can be seen as then the population level objective underlying this model. So given this, we wanted to actually understand what happens when you do minimize this particular objective. And to do that, so I have to always start in a very simple setting. I have to start always in Gaussian, under a Gaussian model. So what we looked at is, for instance, let's say our true distribution mu was, let's say, just for simplicity, zero mean Gaussian with covariance C. We're considering a setup with two data modalities. So we're going to partition this covariance into two blocks. One where the diagonals have a covariance for the marginal of the variable u, one for the marginal of the variable v, and then there's some cross covariance C, I denote by CUV, that relates the two data marginals. And let's say that we look for the encoders GU and GV. This is Gaussian, so we can natural model is to look for a linear encoder, in particular, in this case, some matrix G that multiplies by the random variable U, and some matrix H that multiplies by the random variable V. And what we want to do is find these matrices G and H in order to essentially learn model nu that can approximate this joint distribution mu. If we write down this model nu, it again takes these marginal distributions of U and V and tries to find some way of correlating, of learning the correlation through this density or this tilting of the inner product between GU and HV, which in this particular case, you can really just write as a quadratic form U AV, where A is this inner product of the G and H matrices defining the encoder. So what we're going to look at is what exactly happens. What do we learn about for this matrix A when we minimize losses the loss that appears in contrastive learning. And what we found is the following. So if you minimize the original objective over this matrix, then you get something that's fairly interpretable. So it corresponds to type of normalized cross covariance, the covariance CUV divided by the marginal covariances of U and V. But what was surprising is that if you go back and plug that in to see what is the approximation that results for the conditionals given this choice, it results in the following conditional distributions that have the right conditional mean, but an overinflated conditional variance. So what this means is that what we recover are the conditional means of the true data distribution, but not the variances. So this is a result under assuming that the embedding dimension is fairly large. You can derive a similar what the closed form result is under a smaller embedding dimension, but philosophically it's the same idea. So with this, we wanted to also study what are different variants or objectives that one can construct, because at the end of the day, this is a very particular choice that's been made in contrastive learning to learn with that particular loss. And what happens if you use other losses, and can you actually provide statements about what is maybe you can actually learn the conditional variances correctly, as an example. So what we studied are three different objectives. One is the original objective that tries to match both of the conditionals equally. The second is an objective that maybe just tries to match one of the conditionals. At the end of the day, I believe that there's always some asymmetry in the two conditionals of image and text. One of them has more information than the other. So it's a little bit odd to try to combine the two conditionals in this way that weights them equally to each other. And when I first looked at this problem, the thing that was most natural to me is not to just try to match the conditionals, but to try to match the joint distribution. And I just want to write in words what we show is that when ignoring the aspect of having a low embedding dimension, when you minimize this one-sided objective, you can actually match the conditional mean and the variance of the conditional that you're targeting, unlike the original objective. Of course, that just matches one of them, not both. On the other hand, if you do minimize this joint loss, you can actually provably get closer to the true variances under your data model. So just to see what that looks like visually, this is a very contrived example, but if this was the Gaussian distribution 2D for the two data modalities, if you minimize the original objective, you would get an approximation to the joint that looks like this middle column, has the correct conditional means, but the variances are overinflated. And that's to some degree natural because it's only looking at really conditionals. If you look at this, minimize this joint loss, the conditional means might be slightly off, but it more closely matches provably the variance of the true joint distribution. Yeah.
Perfect.
Okay, perfect. So I just want to now show the numerical results, and in particular going back to these to both a data science application and a science example. So the first is, what are the implications of these different losses for things like data science applications? And what we looked at is, what if the data modalities are image and, for instance, a label associated with that image? So, for instance, in the MNIST data set, you have labels associated with every image. You can train models that predict a label given an image. That's like building a classifier. you can train models that learn images given labels. That's like a generative model, or you can learn a model that tries to match both of these conditionals. And if you look at what are the probabilities associated with each label given a particular image, what's interesting is if you just try to match the label, like build a classifier, it's going to be very confident about one particular label. But if you try to look at other losses, like generative losses or those that try to match both conditionals, they actually introduce some uncertainty we found that I would argue is kind of natural. Like, for instance, in this first row, maybe there should be some uncertainty on that the image is actually an 8 or not just a 3. The last application is this science example. So going back to what we introduced at the beginning, this is this problem of trying to take the trajectories of sea ice flows to ocean currents is something that was originally introduced back in the early 2000s. And most approaches to do this have really relied on having some a model to some oceanographic model to relate tracer positions to currents. But what we ask is if we just have data of many ocean currents from the past and some trajectory data of buoys, could we learn a model that relates these two data sources? And so when I first saw this, I thought of ocean currents. These are like images. These trajectories are like text prompts. And so we can learn a model that relates these two data modalities to each other given pairs of samples. And then solve problems like the one given here, where we take a trajectory and retrieve what is the most likely velocity profile that might have led to this particular trajectory for the buoy over time. I'm just showing here a snapshot. Of course, the ocean is there's a time-dependent field associated with it. The other thing we could look at is how well we can actually perform this retrieval. So this retrieval from on the top row from in both directions. So on the top row, it's going to be the retrieval of a trajectory given velocity field, and in the bottom row, the retrieval of the velocity field given a trajectory. And these are accuracies on the y-axis. The one thing I want to highlight is that you'll observe it is much easier to retrieve tracer positions from velocities than it is to retrieve velocities from tracer positions. And this is expected because the latter is definitely a harder inverse problem. And you could see that directly in the retrieval accuracy as a function of the training of these models. So just to conclude, what I want to summarize is to say that contrastive learning, we showed how the model underlying it is one that builds a joint distribution that learns some type of correlation between the two variables. There is some theory that we can build that shows that these models do learn some properties of the conditional means of the distributions, but not necessarily the variances. And I think this has a lot of downstream applications when we're using a lot of these pre-built encoders for a lot of downstream tasks. And lastly, it does have, of course, applications outside of image and text, and many of you are also using similar models in other contexts. There's a lot of future work extending this to more than two data modalities, I think is interesting. Of course, there's a lot of theoretical questions and looking at other applications, and I'd be happy to discuss more with any of you. So thank you very much.
Okay.